Okay, welcome back. So we're following on from the last kinematics example. Let's see what page this is on. We're on page 10 for our Criterion 5 booklet. And we have another kinematics examples here. So a car travels 50 kilometers north at 100 kilometers an hour, then 30 kilometers south at 60 kilometers per hour. Calculate its average velocity and speed. So let's have a look at the equations first. So remember, our average velocity is equal to displacement over time, whereas speed, speed is equal to distance over time, delta t. And I should have put in delta t's because that's what we have in our notes. So displacement over time for velocity and speed is equal to distance over time. So we need to know what they are in each case. So I'm going to start off by saying that north is positive. So north is positive. So that means our displacement S is equal to 50 kilometers north. 50, I'm going to put in our units here, minus 30 kilometers, because 30 kilometers is in south. And so that's going to be our overall displacement is equal to 20 kilometers north. 20 kilometers north. All right, so our distance, D, is equal to simply 50 kilometers plus 30 kilometers. So all in all, they have travelled 80 kilometers. So remember, with distance, the direction is not important. It's just how far they've gone. So it's 80 kilometers is the distance. Okay, good. So the other thing we need to find in both cases is the time. So this is actually a little bit harder to find compared to the distance and the displacement. So to find, if we start off with, I'm going to start off with the speed formula. If we want to make delta t the subject, we have to swap those two around. So just imagine you're timesing by t and then dividing by speed. So that means that delta t is equal to distance over speed. Okay, so we have to actually look at each case. So that's like one case, and then this is another case here. So the distance in, let's go first one, and that's the second one. So the first case, we have 50 kilometers divided by 100 kilometers per hour. Okay, and then the second case is 30 kilometers divided by 60 kilometers per hour. Okay, so we end up getting 0.5 hours h plus 0.5 hours. So when we divide by this -1, it actually raises it to the top. And that's sort of like the indice laws, but just as long as you remember that the time is in units of, well, time hour. So these are hours, so because we're using kilometers per hour, we're going to end up with hours. So we end up with 1 hour. 1 hour there. So that's our time. Normally we like to use seconds and meters, but if they're all in the same units, we can just keep them as that, as long as there's consistency. Okay, so 1 hour here. And now we can just find out what our average velocity is. So VAV, average velocity, is equal to our displacement S, which is 20 kilometers over 1 hour. So if we have 1 hour down the bottom, 20 kilometers on top, we end up with equal to 20 kilometers per hour. And we need a direction, so north is our direction. Sorry, it's all getting a little bit messy. And now we have speed, which is equal to our distance, which is 80 kilometers over 1 hour, which is equal to 80 kilometers per hour. Okay, so that's our average velocity and speed. So we've ticked those ones off, so we've got that one. So that's how we solve that problem. So a fair bit more work, and this one's a bit simpler, this problem here. An Olympic sprinter is accelerating at 2.1 meters per second squared from rest. So that means that their VI equals 0 meters per second. So that's what the rest, whenever you see rest, you know that its initial velocity is 0 meters per second, or if it goes from a speed to rest, its final velocity might be 0 meters per second. Okay, it reaches a speed of 12 meters per second. Calculate how long this will take him. Okay, so if we remember from a bit earlier, we had average acceleration is equal to change in velocity over change in time. It's equal to 12 meters a second, so it's going to be Vf minus Vi over change in t. I'm just going to leave change in t as is. But we know what the acceleration is. We know what A average is. So we want to rearrange for t. So we end up getting delta t is equal to Vf minus Vi divided by A average, which is going to be equal to 12 divided by 2.1. So that's meters per second. It's our velocity, meters per second squared. And that is going to be, when we put that into our calculator, I might as well do it into the calculator here. So we get 12 divided by 2.1, like this, and that's equal to 5.71. Okay, 5.71 seconds as well. Yeah, so just a couple of, just while we're doing this one, I'll just mention in physical science there's 3. If you go to 3 significant figures, then that's going to be acceptable in all cases. If you notice in our calculator, I'll bring that back up, we can go to many, many decimal places here, and we're not calculating an acceleration for NASA in this example, so we don't need to go to all of these decimal places here. We just probably need to do the first 3. So in this course, technically we only really have 2 significant figures because both of these numbers are given to us in 2. But if you go to 3 significant figures, then that's fine in our course. And I like to, you don't have to put the units in if you can remember what the units here are, but I'll just show you quickly why I like to put in units, because you can see if you go meters, you can cancel those meters out, and then one of these seconds will cancel out with one of those. So we end up getting a minus 1 second on the bottom, and then that ends up becoming seconds on top as well. It's okay if you don't follow that or you don't understand that. Feel free to ask me about that if you like, but you don't have to show that kind of working out, that level of working out in the course. If you end up with 5.71 and you remember it's seconds, then that's all fine. Okay, so they're the kinematics examples. We're moving on to equations of motion in the next video.